So, as we were discussing in class about the down conversion and up conversion mixers, the basic idea is to use the multiplicative property of switches and use that to create your basic mixer cell, and this is called a Gilbert cell mixer. Okay, because it uses the same topology as what was designed for a multiplier a long time ago. That may have been using bipolars, but that really doesn't matter to us. Its basic circuit topology is exactly the same. So, for example, if you have an RX mixer and let us say your signal was at omega RS, okay, and this is your amplitude. You have your LO signal, but as we know, your LO signal could be a square wave, and even if you had a sine wave, a large sine wave, the current waveform is still a signum function, so it's a square wave. So you will have 3 omega LO, 5 omega LO, and so on. You will have the harmonic content of the square wave. Okay. So now you are going to give this to the RF signal. The first one, you are going to give this to the RF port, and you are going to give this to the LO port. Or you might give just a pure sinusoid, but the LO current looks like this. How do you look at the output signal, the IF signal in the frequency domain? In the time domain, you are multiplying these two signals. So in the frequency domain, you are going to convolve these two signals. So you are going to do a convolution of these two. And what you get at baseband or at the IF okay, so what you get at IF is you will get your basic down converted signal at omega IF, and apart from that, what else did we get in a single balance mixer? So let us say this is a single balance mixer. You get omega LO, what else do you get? You get the other side. You get omega LO plus omega IF on the other side. Sorry, omega LO plus omega RF on the other side. Apart from this, you also have, I'm going to draw it slightly enlarged scale. You have 3 omega LO. Okay, and 3 omega LO mixed with omega RF is going to give you some sideband, and you're going to have 5 omega LO, and you're going to get sidebands based on that, and so on. Right? Each of these components is going to convolve with your desired RF signal to create sidebands on either side. Technically, what you can do is do something like this: get a nice filter going at your IF frequency, which will remove all the unwanted signals. If you want to make sure your LO feed through is not there, you have to use a double balance structure. It will still give you some of the other components. The upper sidebands and lower sidebands cannot be removed. You will still get the mixing products. You will have to deal with them through some kind of filtering. Okay? And to quickly review the other items we saw, we did the mathematical analysis of the single balance mixer by treating the current function as a signum function. We derived the Fourier series of that function. Very simple, you've all seen that before. And based on that, we said the input has a DC component and a signal component, so it's IDC plus IRF cos omega RFT. We multiplied that with the Fourier series of the switching function, of the signum function, and it had two sets of terms. The first set of term was IDC times S of t, so that gave you all the LO feed through terms. The second function is IRF cos omega RFT times the Fourier series of your switching function, and that gave you your mixing terms with LO, 3LO, 5LO and so on. Right? That is what we derived. And finally we took the desired receive term in this case, and we said that for the single balance mixer, the overall gain of the single balance mixer, the conversion, the voltage conversion gain is 2 IRF by pi with respect to the current. Right? If your input current is IRF cos omega RFT, the output current is 2 IRF by pi cos omega IFT. Finally, if you are going to generate this IRF using a transconductance, you will have some GM. If you are going to take the load current through a resistor, some resistive load RL, you can write your voltage conversion gain as 2 by pi GM RL. And there are many different ways of generating this transconductance. We are going to see some of those today, but the more important circuit we looked at last time was the double balance mixer. The basic idea was that since you still have your LO feed through components which could be close to your IF frequency, you don't know, because in different cases you might want to choose IF and LO differently. You don't necessarily want these LO feed throughs in your output, and therefore there is an easy solution for this. The easy way to do this is have the RF portion as a differential input, so you have an plus or minus IRF cos omega RFT, and you take two copies of the same mixer, and to one mixer you give LO plus and LO minus, to the other mixer you swap the LO input, so which gives you a negative LO feed through term, and then you add those two to create you add the two output currents, two sets of output currents, to give you the overall output which does not have the LO feed through. And we actually drew the circuit. It's just a simple modification of what we had, and we also worked out the math. It's very simple, and as you can see, the LO feed through is completely dependent on the matching between the two paths and nothing more, between the two mixers. The conversion gain is also a little bit larger as expected, because now you have two sets of transconductors, you expect twice the gain, and that is as expected. Finally, for the double balance mixer, the isolation is dependent on many things. First of all, the LO waveform. Second is the LO device mismatch, the RF device mismatch, and the load mismatch. It is a function of all of these. So in today's class, we'll start looking at how to design these RF transconductors which you need for these mixers. Obviously, the simple transconductor we looked at was the common source transistor. So you give a Vn. I'll omit all the bias details. I assume all of you can add the bias details very easily. So you give an input signal Vin, the output current is Gm times Vn. As expected, you can design the transistor for a given Gm. How do you control the linearity? Now note that in the case of the mixer, we are going to approach things slightly differently. In the case of the LNA, noise was paramount, right? So we did all the noise analysis up front, right? And then we went to linearity and said, okay, Your noise is most important. You are going to design your circuit for noise. Linearity will take a little bit of a backseat. It's important, but it will take a little bit of a hit. Not hit, but it's less of less importance than the noise. On the other hand, the mixer comes down the chain. Therefore, its noise is less important, but its linearity is more important. So we need to look at those aspects first before we look at the noise. So how will you characterize the linearity of this common source? Again, what kind of linearity are we talking about first? Linear transconductance. Anything else? Let us say the transconductance is perfectly linear. Does that mean your overall mixer is perfectly linear? So far as we have seen, yes. Right? If your conversion from VRF to IRF is perfectly linear, we have seen that if the mixer has ideal switches, it is just a multiplication and there is not much more to it. Unfortunately, we do know that these mixers, if you use real devices, they will not be ideal switches, and there will be, or there could be some hit to linearity. We are going to look at that today. But apart from that, so how would you characterize the linearity of the mixer? We have seen it's through IIP2, IIP3 and so on, right? So let us take the case of a super heterodyne receiver where we are interested in IIP3. So what parameter are you interested in as far as this MOSFET is concerned? GM gives you the conversion gain. What aspect decides the linearity of this device? The resistance. No, that is not what I am looking for. You are interested in IIP3. You are interested in GM3, which is, we have seen this before. You are interested in GM3, which is at a given VDS. Is VDS fixed? So let us go back to our single balance mixer. Or yeah, is the VDS of this device fixed? If you have ideal switches, VDS will be almost fixed. So okay. So let us say this was the signal going here. This was the signal going to LO minus. If you have ideal switches which switch instantaneously, you have the square wave has no rise or fall time. What happens? At any time, either M2 or M3 are on. Correct? Either M2 or M3 are on at any time, and since they switch instantaneously, they are going to be in saturation. Correct? They are going to be in the saturation region with a well-defined bias current, which is the bias current through M1. Correct? So they have a particular VGS. When it's on, what is the gate voltage? Let us say it's VDD, or let us say it's some V0. Why say VDD? Let us say it's some V0. The voltage here will be V0 minus VGS23, right? And as long as they switch instantaneously, either one of those devices will be on, it will be constant, right? If they don't switch instantaneously, what happens? You could have both could be on at the same time. So effectively what will happen is, you will see some kind of variation in this voltage. It will be there are two aspects to this. First of all, as the rise time and fall time of the LO waveform get smaller and smaller, right? These regions will also get smaller and smaller. But more importantly, this variation around the mean value will be periodic, right? Because every half period, one of the devices will go from on to off, the other device will go from off to on. So what kind of behavior, what kind of periodicity do you expect for this? It will be at double the frequency. So you may see something like this, where from here to here is the LO period, correct? And you can take the average value of this to actually figure out what the DC value is. But these, as long as the rise and fall times are small, what other conditions are there? Rise and fall times should be small for the LO waveform. Is there any other condition? Symmetry, okay, let's assume, I'm already assuming they're symmetric. Obviously, if they're not symmetric, again you will have some residual waveform here. Anything else? What should swing as high as possible? Perfect. So the LO waveforms, so let us look at this. So let me copy this. So we have seen two aspects here. So okay, you want small rise time and fall time. Symmetry. What else? Very large. Large V naught. I'll just say large LO amplitude. But really, what does large mean? Large is a very vague term, right? So when you say something is large or small, it's always relative to something else. It should go to supply. Is that right? It should act like a diode. It should be in? Should be in triode or cutoff? No. No, the device should never be in triode. It should go from, it should be in either cutoff or saturation. In this device, in this active mixer, the switch should never go into triode region. Okay, remember, look at it this way, right? Let us say M2 was on and M3 was off. All of the current is flowing through M2. Okay, M2 is on, but if the output swings low enough such that M2 goes into triode, right, then there will be linearity concerns for both M1. Okay, for M1, as well as there will be concerns about other aspects of the circuit which we will not get into right now. But you definitely don't want M2 and M3 to be in the triode region, because it's an active mixer. You're using the switches as a current switch and not as a resistive switch, where when it's on it has a very low resistance, when it's off it has a very high resistance. Okay, in other words, when the device is on, you want it to behave like a cascode device, in other words, right? So when you say large LO amplitude, what is it relative to? It should be sufficient to steer the current. Exactly. So when you say it is large, it should be large enough to sufficiently steer the current very fast between M2 and M3. Correct? How do you decide what amplitude is large enough? So the amplitude will be such that when M2 is on, then the full current, that is the bias current, completely goes to M2. When does that happen? That will happen when the variance of that becomes equal to a value pertaining to the current of I naught or something equivalent. Huh? M2 will go to or M3 will go to cutoff. Correct. But when does that happen? If I have a differential pair with a bias current I naught, at what differential input will the current completely steer one side? Root 2 times VGS minus VT. Okay. So sorry. at V naught equal to root 2 times VGS minus VT. Okay. So I need some more space, so I'm going to move this up. Okay, that's fine. So full current steering happens at root 2 times VGS minus VT. So what do I mean by large amplitude now? That I understand. So we have said that full current steering happens when V naught is root 2 times VGS minus VT. So if you really want a good mixer, your your LO amplitude should be at least root 2 times VGS minus VT. I hope you agree. What happens if V naught is less than root 2 times VGS minus VT? Okay, so what? It will be like a differential operation. What does that mean? Why? No, I understand all of that. Of course, if it is less than root 2 times VGS minus VT, the current will not switch completely. So what? Let us go back to this guy. If I look at S of t, what will happen in this case? Or you can even look at S1 of t if it is easier, because you are looking at only one side. What will the current look like? It will have a DC offset. It is like shifting the square wave, right? In other words, you won't be switching all of the current, you are only switching part of the current. The other part of the current acts like a DC offset. Okay, what does that mean for us? Okay, anything else? It will affect your feed through. Anything else? Now you will need to find out the Fourier series of this new square wave, whose amplitude will be smaller, because the switching component, the maximum current will not be, it won't swing between 0 and plus IDC or 0 and plus IRF. It will swing between maybe 0.1 to 0.9 or 0.2 to 0.8 or something similar, depending on how much of the current switches. In other words, it will no longer be the pure signum function, it will be a scale signum function. And if you look at the Fourier series of S of t, the Fourier series components will be smaller, and therefore your conversion gain will be smaller. Is that clear? So instead of getting from a single balanced mixer, instead of getting 2 IRF by pi, you will get something smaller. Okay, so we definitely need at least root 2 times VGS minus VT. How do you ensure that you get at least root 2 times VGS minus VT? Make it swing to VDD. Okay, so that is one option. Okay, make very large. What do you do if VGS minus VT is close to VDD? Obviously there are two sides to it. One is use a large LO amplitude. The other is design the LO switches with very small VGS minus VTs, very small overdrives, so that they switch very fast. So you want large LO amplitude plus small VGS minus VT for the LO, right? So when you say you want a large LO amplitude, you want it large, very large compared to root 2 times VGS minus VT, so that the devices spend as little time as possible in the when both devices M2 and M3 are on at the same time. That is what you want to prevent. Okay. and having very small TR and TF will also accomplish the same thing. Okay, so now we have some idea of how to design the LO switches also. So now let us go back to the RF transconductors. So you are interested in GM3 because this will give you an idea of what the IIP3 of the overall mixer is going to be. So what is the GM3 for a MOSFET, for a common source MOSFET? What is the GM3 for an ideal square law MOSFET? It is 0 because it has only a quadratic behavior. The current to voltage is purely quadratic. You will not have a GM3 term at all. Agreed? Suppose I had a pseudo differential common source pair. What is the IIP3 of this? Again, infinite, as long as they are purely square law. If I bias it using a current source, what is the IIP3 of this? It will not be infinite. This will necessarily have a third order term, okay, because the output current to input voltage behavior is no longer decided only by the device characteristics. It actually depends on the differential input voltage instead of just the single-ended input voltage. Therefore, you will necessarily have the third order term. In fact, in this case, you will not have the second order term as long as there is good matching between either side. How do you improve the linearity of this? So, obviously, if you have a common source transistor, let us just go back to this case. Let us consider the common source transistor, which is not purely square law, because most of the short channel MOSFET you use will not be purely square law. What will be how do you look at the IIP3? You will have to characterize dou cube ID by dou VGS cube for the given VDS. The reason we started off with the sidetrack on the mixers is to decide whether VDS is constant or not. What you know is that VDS is going to be more or less constant. Okay? So you can figure out for that VDS what the GM3 would be. Okay, so you can characterize the third order nonlinearity of this. Of course, we have seen before that you can bias it such that it has very low third order nonlinearity. Apart from that, can you do anything else to help? You can use a feedback loop. Okay. Now, if you look at a receiver, this input is actually VRF, this output is actually IRF. Right? At these frequencies, feedback will not be effective, or at least complex feedback will not be very effective. What else can you do? You can degenerate the common source. So that is of course one kind of feedback, right? Except it's not a complex feedback. You can use degeneration. Okay. What is IRF? If let's say this was RE, what is IRF? GM by 1 plus GM RE. Okay. This is your transconductance. How do you make it more linear? The larger you make the GM of your device. So if I say, again when you say large, it has to be relative to something. 1 by RE. if Gm is made very large compared to 1 by Re, sorry, Gm by 1 plus Gm Re times Vrf, why is this more linear? Because by definition a resistive element is as linear as you can get in most cases. However, remember the resistive elements on an IC are generated using diffusion, right? Silicon, doped silicon, either in the substrate diffusion, maybe an N-well, or the polysilicon. All of these will most probably have some kind of voltage dependence, and therefore this is not necessarily 100% linear, but it will be much more linear than your MOSFET. That much you can tell. That much you can say. So this is one possibility. What are the downsides of this? Headroom is one thing. Headroom is lower. Anything else? Noise. Noise is worse. Right? These are the two biggest problems. How do you fix this? Okay, let's start off with headroom lower. Can you get degeneration without losing headroom? You can use inductive degeneration, right? So now I can use inductive degeneration, which will give you better headroom. There is zero DC headroom loss, and there is no noise also from the inductance. The overall Gm of this will be Gm by S square Ls Cgs plus S into Gm Ls plus 1 times Vrf. Okay. Now, in combination with CGS of the transistor, this is obviously a second order system. Remember that. If you look at the effective transconductance, again in a log scale, it will look something like this, and depending on the relative values of Ls and CGS and so on, you can have other peaking behavior also, but we'll look at the simplest behavior, which looks like this. The important thing we are looking for is also the fact that this actually gives you a two-pole roll-off out of band. Okay? So if you have any high frequency content, for example, maybe the LNA gives you a third harmonic and you want to get rid of it, you can use this kind of inductive degeneration to give you better attenuation of those third order components, as long as you choose Ls carefully. Obviously, for higher frequencies, it is expected that it gives you better rejection, because the impedance of the inductance increases with frequency, so it is as if you have a frequency dependent degeneration. At very high frequencies, the inductor acts as an open, therefore you have very little gain. This is obviously expected. So good attenuation at higher frequencies. no headroom loss. No noise is added. So these are all the plus sides. What are the minus sides? Obviously area is number one. Anything else? Any other issues you can think of with this? Huh? It's narrow band. Why is it narrow band? As far as I can see that the effective GM looks like this. It is not necessarily narrow band. However, the GM effective itself may look like this, but as he says, the degeneration effect, so the effect on linearity will happen only over a range of frequencies. Obviously at very low frequencies the inductor is short, you get no degeneration at all. Okay, so GM effective may look like this, but GM3 for example if you plot it, it will be frequency dependent and it will help only over a narrow range of, relatively narrower range of frequencies. Anything else? Any other issues you can think of? That should be something very obvious when you look at it. Look at the circuit and tell me what does this look like? This looks like the input match of an LNA, of a common source LNA. What do you know about that? It has a real input part. Do you want a real input part here? You don't. Okay, you do not. So far I have been assuming that the mixer LNA output is directly driving the mixer. You wanted only capacitive input. If you have a real part, what happens? So the omega t ls real part will degrade the Q of the LNA output resonant circuit. Okay? For example, let us say you had designed your LNA output resonant circuit such that it's the impedance of the resonant circuit at resonance was, let us say, 300 ohms. But let us say this omega t times Ls gave you another 300 ohms. The effective impedance, parallel impedance will only be 150 ohms. The gain of your LNA just became half of what it used to be. The minute you tag this mixer at the output of the LNA. Okay? So this is obviously a problem, right? Because you can't expect, you primarily expected a purely capacitive input. You are now getting a real part, which is DQing it. What other kinds of circuits have you looked at? So we looked at the common source with degeneration and so on. What other kinds of transconductors do you know? A common gate can act as a transconductance also. So let us say I take my input, yes. If you do that, you will get a negative portion which you can use to cancel the positive portion. How is that what you want to do? So what will happen is over the region of resonance you will get very high impedance. At all other points you will get low impedance. The only thing you have to be careful about, the minute you put a capacitor at very high frequencies, the input will be purely, the resonant circuit will be purely capacitive, so your input impedance will become negative. Okay, you don't want to start oscillating at the LNA output. That is the only drawback I see with that. So let us say I take the common gate transconductor and I apply it through a resistor to the gate of the to the source of the common gate. What is the effective GM? It's GM by 1 plus GM RS plus SRS CGS. If GM was much larger than 1 over RS, right, the effective GM will just become 1 over RS at low frequencies when CGS effect is very small, correct? Correct. Yes. So that is why the input overall transconductance will just become 1 over RS. You understand? I am applying it through a resistor. So the effective current into the common gate would have been VRS over RS plus 1 over GM. Okay. If I make 1 over GM very small compared to RS, it will just become 1 over RS times VRS. And all of that current flows through the common gate into the output. So of course you can put in the sign this way because you are applying a voltage and creating a current. Now if I plot GM effective as a function of frequency in the log-log plot, I'll get something like this. Since it's a single pole system, I know that I'll get a minus 20 dB per decade roll off. At low frequencies, I know it's approximately 1 over RS. What is the pole frequency? Is omega t. Of the device itself. Okay? The pole frequency will be just omega t because it is just CGS in parallel with 1 over GM in parallel with RS. 1 over GM will dominate and it will just be GM over CGS. So this is obviously a very wideband transconductor. What is the problem with this again? Does it take up any headroom here? It doesn't because you are AC coupling it through a capacitor. You don't care about the headroom. Does it add noise? Of course it does add noise. Any other issues? Of course, it will load the LNA, right? So those issues are still there. Loads the LNA output. The only difference is now you can choose RS large enough such that it doesn't load the LNA output, but you still get sufficient transconductance. If you can achieve that balance, then you are good to go. What is the gain of this mixer? The conversion gain of this mixer? 4 by pi RS. It will be 4 by pi RL by RS. Right? The conversion gain has to be dimensionless. The conversion gain of a mixer using this transconductance would be 4 by pi RL by RS. Right? So you will have to get, if you want to get enough gain, conversion gain from this mixer, you will have to choose a small RS. If you don't want to load the LNA, you will have to choose a large RS. Right? So that is your trade-off right there. And again, RS should be much larger than 1 over GM. So you want RS to be large enough such that you don't use a lot of current. Okay? Now you can look at other transconductors as variations of either the common source or the common gate. You can build differential versions of the balanced with inductor degeneration and so on. one last thing I wanted to cover is actually two things. Let us take the case of something like this as an example. Let us take a differential transconductor with inductive degeneration. So, suppose I have these unwanted frequencies at which I want to reject the gain of this circuit. There happens to be an easy way to do this, which is by adding a parallel resonant circuit in series with these with the ground connection. For example, you can add two of these. There is no DC headroom because of the inductor, but you can tune these to F1 and F2, where these two are unwanted frequencies. Okay? In other words, at these two unwanted frequencies, there will be no RF current flowing through these because this will look like a high impedance. So this is one aspect which is used in many different kinds of circuits. You can use something like this. This is called harmonic filtering. You can use this in many different kinds of circuits. As you will see, this is used in other circuits like power amplifiers also to reject unwanted harmonics. Now, finally, I wanted to talk about what is called the multi-tarnished transconductor. Do you have 5 more minutes? Any of you have a class after this, immediately after this? You have a class now? Okay, I'll take 2 minutes, finish this up, and then we'll stop. So, I'm going to take 3 of these circuits. Okay, so VRF minus VRF, and I'm going to apply the same inputs to all of these. The only difference is what I'm going to do is I'm going to add up the outputs in such a manner and I'm going to make these 1:1, 1:A and A:1. I'm going to size these differential pairs in such a manner. Okay, the first one is going to be completely symmetric, the second one is going to be biased in one direction, the third one is going to be biased in exactly the opposite direction with the same bias current. If I do this, if you plot the overall ID versus the input differential current, the 1:1 transconductor will look like this. So I'll call that 1, 2 and 3. The basic 1:1 will look like this. The second one will be offset in this way. So this is 1, this is 2, and the third one will be offset in this manner because of this biasing. And now if you actually plot the overall transconductance of this as a function of VIB. Okay, so the first one, will look like this. This is 1. The second one will look like this. Sorry, the third one will look like this. The second one will look like this. And if you plot the overall transconductance, you are trying to get something which looks like this, which you get a very good transconductance, a very linear transconductance over a wide range of input voltages. So in other words, you are increasing the input dynamic range, right? Even if you apply a very large input signal, you will still get a large GM. Okay. The reason, of course, this is called a multi-tangent circuit is if you look at a bipolar transistor, the differential transconductance of a bipolar transistor, the differential current to voltage behavior is a tan hyperbolic behavior. So therefore, you can, therefore this is called the multi-tangent circuit. Okay. So we will stop here, and tomorrow's class, on Monday's class, we'll finish up on this nonlinearity of the mixer, and we'll start off with mixer noise.